Hello everyone, I'm Shuwei Chaoshen. Today we'll continue our series on essential topics for 10th grade. We'll be looking at the monotonic intervals of composite functions involving logarithmic structures, specifically how to determine their monotonicity. For composite functions, we still follow the rule of same increase, different decrease, but you must never violate the domain of the function. This means when studying these logarithmic functions, you should write out the domain first. Let's take a look. F of x is equal to this. Log of x squared minus 2x minus 8. Now, the argument of the log must be greater than 0. So that means we can deduce that x squared minus 2x minus 8 is greater than 0. This means if we factor it slightly, we get a quadratic inequality in terms of x. It must be greater than 0. So let's draw the corresponding quadratic graph. One root is negative 2 and the other root is 4. We need the parts greater than 0. So that means your x must be less than negative 2 or x must be greater than 4. All right, so with that, let's denote this composite function as y. Then we write the inner layer, t, which equals x squared minus 2x minus 8. It's a parabola opening upwards. However, note that the interval between negative 2 and 4 is excluded. So, looking to the left and right, we can find its monotonic intervals. From negative infinity to negative 2, it's decreasing, so it's monotonically decreasing. From 4 to positive infinity, it's rising, so it's monotonically increasing. As for the outer layer, y equals log t, this logarithmic function is always monotonically increasing. So combining them, from negative infinity to negative 2, we have a decrease and an increase, which results in a decrease. From 4 to positive infinity, both increase, so it's an increase. Thus, the monotonic increasing interval is 4 to positive infinity. We choose option D. That's the first example of the same increase, different decrease rule. Okay, now let's take a look at this. Quick practice problem. It gives another function, f of x, and says it's monotonically increasing on the interval from 2 to positive infinity. Now, what is the range of the real number a? Well, it's the same process. The inner layer is quadratic, so t equals x squared plus ax minus a minus 1. The outer layer is y equals log t. Since the outer layer is always monotonically increasing, it means I only need to ensure that this quadratic function is monotonically increasing on the interval from 2 to positive infinity. This quadratic function opens upwards, and its axis of symmetry is negative b over 2a, which is negative a over 2. To ensure it's monotonically increasing from 2 to positive infinity, 2 must be to the right of the axis of symmetry. So that means 2 must be greater than negative a over 2. Being equal is also okay. The endpoint being equal doesn't affect monotonicity. Besides that, you'll find that for all numbers from 2 to positive infinity substituted for x, you must ensure the argument is greater than 0. That's the domain constraint. So let's plug in 2. 2 squared is 4, plus a times 2 is 2a minus a minus 1. Now, note that since this is an open interval, it means even if it's exactly 0, it's still fine. Plugging in 2 gives 0, but 2 isn't included, so it's greater than or equal to 0. So in this case, multiply both sides by 2. 2 times 2, 4 must be greater than or equal to negative a, which means a must be greater than or equal to negative 4. The second one is 2a minus a, which is a, plus 4 minus 1 is plus 3, greater than or equal to 0, so it must be greater than or equal to negative 3. 1 is greater than or equal to negative 4, the other is greater than or equal to negative 3. Take the larger one, so finally we need greater than or equal to negative 3. The answer is option B. So overall, we must consider the domain restriction here. Okay. For monotonicity studies, whether finding intervals or solving for parameters given monotonicity, the approach is the same.